"Look at this," the message said, and Evo Lab looked. It was July 2022. 1 week had passed since the James Webb Space Telescope released its first images to the world, and somewhere between those images and what Lab was about to find on his screen, the oldest argument in cosmology was about to get a new piece of evidence that nobody had a ready answer for. The cosmic microwave background, the oldest light in the universe, the glow left over from 380,000 years after the Big Bang had been telling astronomers for decades, when the first galaxies formed, how fast they grew, when they cleared the primordial fog. Webb was about to say something different. Not loudly, not in a press release. In 2 numbers on a screen in Melbourne, in the middle of an ordinary working week while a man was drinking his coffee. That conflict between the oldest light and the newest findings is what this story is actually about. Not the record-breaking galaxies, though those are real. Not the headlines about the Big Bang being broken, though those traveled far. The actual story is quieter and harder to resolve, and it starts here, in this moment, before anyone knew what was coming. Barely a week had passed since the press conferences happened. The politicians had stood at podiums. The adjectives had been used. And now the scientists were doing what scientists actually do after the cameras leave, which is sit at their desks and run the pipelines and wait for the numbers to come back. Lab was at his desk at Swinburne University of Technology in Melbourne, working through the first raw imaging data. This is the part that does not make the press releases, the part where you take what the telescope sent down and you feed it through analysis software and you look at what comes out. And most of the time what comes out is roughly what you expected. And you move on to the next thing. He was not alone in doing this. Dozens of teams around the world were doing the exact same thing in the exact same week. All of them running pipelines on the same images. All of them looking for different things. All of them hoping to find something that would justify the wait. Erica Nelson was at the University of Colorado in Boulder. She and Lab had known each other for 15 years. Since she was a first-year undergraduate at a small liberal arts college in California, and he was a newly minted PhD, doing his first postdoctoral work in Los Angeles. They had orbited each other through the years in the way that scientists do different institutions, different projects, converging on the same questions from different directions, and now here they were at the tip of the spear, both of them working on the first data from a telescope they had been waiting their entire careers to use. She was looking at a set of objects she had started calling UFOs, ultra-red flattened objects. Galaxies that appeared in the infrared but were invisible at wavelengths the human eye could see, and that appeared in the images as flat, disc-like shapes, like flying saucers. She was cataloging them, characterizing them, doing the work. Then she sent Lab a message, just those 3 words. "Look at this." He looked. One of the objects in the data was not a flying saucer. It was a small red dot, a pinprick. He ran his software on it. The software returned 2 numbers. Distance, 13 billion light years. Stellar mass, 100 billion times the mass of our sun. He nearly spilled his coffee, not because the numbers were large. Lab had spent his career working with large numbers. The universe is full of large numbers, and most of them are not surprising. What was surprising was the combination, the distance and the mass appearing together in the same object at the same time. A galaxy 13 billion light years away is a galaxy we are seeing as it was 13 billion years ago, when the universe was very young. The universe is 13.8 billion years old. A galaxy 13 billion light years away is a galaxy we are seeing when the universe was less than 1 billion years old. And a galaxy with 100 billion solar masses is a galaxy with as many stars as the Milky Way has right now. Today, after 13.8 billion years of star formation. Those 2 numbers, appearing together, said something that the models said was not supposed to be possible. A galaxy the size of the Milky Way should not exist when the universe is less than 1 billion years old. The physics of the thing does not allow it, or rather, the physics as astronomers understood it did not allow it. Stars form from hydrogen gas, and the early universe had plenty of hydrogen. But it takes time to assemble that hydrogen into galaxies, and it takes more time for those galaxies to build up stellar mass, and the rate at which gas turns into stars has limits. Hard limits. Limits that the models had been calculating for decades. And those limits said that a galaxy with 100 billion solar masses in the first billion years of cosmic history required a near-perfect conversion of all available gas into stars at efficiencies that were, as Lab would write later, very hard, which is the scientific term for impossible. He went looking for more. The next day he had found six objects, all of them red, all of them small in the images, all of them sitting at distances that put them in the first 5% of the universe's age, all of them apparently carrying stellar masses that should have taken far longer to accumulate than the universe had given them time to accumulate. 6 objects that the models said should not be there, and yet there they were, in the first week of data from a telescope that had not yet finished warming up. He wrote about it later in plain language so that people outside the field could understand what he had found. He used the word impossible. He used it not as a figure of speech, but as a precise description of what the numbers were saying, that the thing in front of him was not permitted by the framework that had been built to explain how the universe works. One of the 6 candidates, when a spectrum was taken, turned out to be a quasar, rather than a galaxy, an actively feeding black hole whose brightness had been mistaken for the brightness of a massive stellar population. 1 black swan down, 5 to go, he wrote. But he was not relieved. He was more unsettled than before, because a quasar at that distance and redshift was its own kind of impossible. Its own set of questions that the models did not have ready answers for. What happened next is what always happens when a finding is too strange to ignore and too early to be certain about. The community absorbed it. Teams with more resources and more telescope time began following up on the candidates with spectroscopy, the technique of splitting a galaxy's light into its spectrum and reading the fingerprint of its chemistry and its velocity to get a precise distance measurement rather than a photometric estimate. Photometric redshifts are approximations. They are good approximations, good enough to identify candidates, but they can be fooled. A galaxy at moderate distance with unusual chemistry can look, in broadband images, like a galaxy at extreme distance. The follow-up spectroscopy was necessary before anyone could say with confidence that what Lab had found was what it appeared to be. Some of the candidates did not survive the spectroscopy. They turned out to be closer than the imaging suggested. Interlopers from the middle distance masquerading as objects from the cosmic dawn. This is normal. This is the work. You find candidates and then you confirm them, and some survive and some do not. And the ones that do not teach you something about the limits of your selection technique. But some of them survived, and the ones that survived were, if anything, more unsettling than the original photometric estimates had suggested. Because the spectra did not just confirm the distances, they revealed the chemical composition of these early galaxies. And the chemical composition was wrong in ways nobody had predicted. This is where the story branches into something that took 3 more years to fully understand, and that as of the middle of 2025 is still not fully understood, and that may not be fully understood for another decade. But to follow the branch, you have to first understand what was there before Webb arrived. You have to understand what the models were built on, what measurements they were calibrated against, and why those measurements seemed, for the better part of 3 decades, to be sufficient. You have to go back further than Lab's desk. You have to go back to the oldest light itself. The oldest light in the universe is not a galaxy. It is not a star. It is not any object you could point a telescope at and say there. It is a glow, a remnant, something left behind when the universe was 380,000 years old, when it had cooled just enough for protons and electrons to combine for the first time into neutral hydrogen atoms, and when all the photons that had been trapped in the hot, dense plasma of the early universe were suddenly released, free to travel, free to move through space in every direction at once. That moment physicists call it recombination. Though the name is misleading because the protons and electrons had never been combined before, was the moment the universe became transparent. Before it, light could not travel. The universe was opaque, a fog so dense that photons could not move more than a short distance before being absorbed and re-emitted and absorbed again. After it, the universe cleared, and the light that was released in that clearing has been traveling ever since, traveling for 13.4 billion years. It is still here, all around us, all the time, arriving from every direction in equal measure. A bath of microwave radiation that you can detect with the right instruments and that carries, encoded in its temperature variations, the precise fingerprint of what the universe looked like when it was 380,000 years old. This is the cosmic microwave background. This is what cosmologists mean when they say the oldest light. Not the oldest galaxy, not the oldest star. The light from the moment the universe first became possible to see, stretched by 13.4 billion years of cosmic expansion from the high-energy glow of a young hot universe into the cold microwave hum of the one we inhabit now. The CMB is not just a picture, it is a measurement device of extraordinary precision. Its temperature fluctuations, tiny variations of 100,000th of a degree from one patch of sky to another, encode the density fluctuations of the early universe, the seeds from which all structure would eventually grow. To measure those fluctuations with the precision that cosmology required, it took decades of satellite missions and the careers of hundreds of scientists. George Smoot and John Mather won the Nobel Prize in Physics in 2006 for their work on the COBE satellite, which first mapped those fluctuations in the early 1990s. Smoot described the CMB map as looking at the face of God. That was not theater. It was the recognition that what COBE had measured was the starting conditions of everything, the initial density variations that gravity would spend the next 13 billion years amplifying into galaxies and galaxy clusters, and the large-scale structure of the cosmos. After COBE came MAP, and after WMAP came Planck, the Planck satellite, a European Space Agency mission that observed the CMB between 2009 and 2013, produced the most precise map of the oldest light ever made. The Planck collaboration, hundreds of scientists across Europe and beyond, spent years processing and analyzing that data, and in 2013, and again in 2015, and again in 2018, they published results that gave cosmology its most precise set of foundational numbers. The density of ordinary matter, the density of dark matter, the density of dark energy, the rate of expansion, the age of the universe. These numbers, extracted from the temperature variations in light that is 13.4 billion years old, became the bedrock of the standard cosmological model, the framework against which everything else in observational cosmology was measured. One of the things the Planck data told us is when reionization happened. Jan Tauber is a Planck project scientist at the European Space Agency. He has spent the better part of 2 decades working on CMB measurements. And when the Planck collaboration published its final results on the optical depth, to reionization, the specific measurement that tells cosmologists when the universe's hydrogen fog was cleared, Tauber and his colleagues understood what they were establishing. Not just a timeline, a constraint, a hard boundary that galaxy formation models would have to respect. The optical depth measurement from Planck pointed to a reionization epoch that ended approximately 1 billion years after the Big Bang. This number was not pulled from a model. It was read directly from the light of the oldest observable event in cosmic history. It was as direct a measurement of reionization's timing as physics allows. Reionization is the period after the first stars formed, somewhere around 100 million years after the Big Bang, when the radiation from those stars was energetic enough to split the neutral hydrogen atoms of the universe back into protons and electrons. This was the last major transformation the universe underwent. Before reionization, the universe was filled with a neutral hydrogen fog that blocked light from traveling freely between galaxies. After reionization, the fog lifted. The universe became transparent again, for the second time, and it has remained transparent ever since. The timeline of reionization matters enormously because it determines when the universe first became possible to observe in the way we observe it now, through the light of distant galaxies traveling unimpeded across billions of light years. It also constrains how many early galaxies there could have been and how bright they could have been. To clear the hydrogen fog in the time Planck's measurement implied, you needed a certain number of galaxies producing a certain amount of ultraviolet radiation at a certain rate. The galaxy formation models built on the Planck data were designed to produce exactly that many galaxies, no more, no fewer, because the CMB was telling you what the answer had to be before you started. This is the circularity that Webb broke open. The models were not wrong because someone made an error. They were wrong because they were calibrated against measurements made before we could see the early universe directly. And the early universe, as it turns out, was not waiting for our models to be ready before it decided what to do. Julian Muoz is an assistant professor of astronomy at the University of Texas at Austin. He is in his early 30s, careful with language in the way that people are careful when they know that imprecision in a field this contested will follow them. He works at the Cosmic Frontier Center at UT Austin, and in the summer of 2024 he spent several months at the Kavli Institute for Theoretical Physics in Santa Barbara, sitting with the Webb data and doing the accounting that nobody in the field had yet done plainly enough to publish. The accounting works like this. You know that all the hydrogen in the universe was neutral before reionization. You know that each hydrogen atom requires a specific amount of extreme ultraviolet energy to ionize. So you can calculate how much total ultraviolet radiation was needed to complete reionization. It is a fixed number, constrained by the amount of hydrogen in the universe, which is itself well measured. Then you look at what Webb has found, the abundance of early galaxies, their brightness, their ultraviolet luminosities, their apparent ionizing photon output. And you ask, given what Webb is showing us about how many bright galaxies existed in the early universe, and how much ultraviolet radiation they were producing, when would reionization have been completed? He did the calculation. He published the result in October 2024 in monthly notices of the Royal Astronomical Society. With co-authors John Chisholm at UT Austin, Jordan Morocha at NASA's Jet Propulsion Laboratory, Stephen Furlanetto at UCLA, and Charlotte Mason at the University of Copenhagen. If you trust James Webb blindly, Muoz wrote, reionization ended 550 to 650 million years after the Big Bang. Not 1 billion years. 350 million years earlier than the Planck measurement says it should have ended. 350 million years is not a rounding error. It is not a calibration issue that will be resolved by better instruments. It is the two most important observational anchors in modern cosmology, the oldest light and the newest telescope, pointing in opposite directions with no obvious reason for either of them to be wrong. Muoz was careful about what the discrepancy means. He did not claim the CMB measurement is incorrect. He did not claim Webb is finding phantom galaxies. He said there is a tension, and that resolving it is a key step to finally understanding this pivotal period. His co-author Chisholm was slightly more direct. Webb has revealed that bright galaxies are enough to ionize the universe by themselves. This is counter to what many people anticipated. Counter to what many people anticipated. Sit with that for a moment. Not counter to a fringe theory. Counter to what many people, the people who built the models, who published the predictions, who calibrated their frameworks against 3 decades of the best cosmological data ever collected, anticipated. Chisholm was describing the failure of a consensus. He was describing it in the mildest possible language because he lives inside that consensus and understands that the failure is instructive rather than catastrophic. But the mild language should not obscure what is being said. The people who built the best galaxy formation models in the world expected the early universe to look a certain way. Webb looked. It does not look that way. To understand why this landed the way it did, you have to understand what those models were built on and who built them. Sandro Takela is a researcher at the Kavli Institute for Cosmology at the University of Cambridge. Brant Robertson is at the University of California, Santa Cruz. Lily Whitler worked on early galaxy formation predictions that appeared in the literature before Webb's first science results. These are not peripheral figures. These are researchers whose published predictions of how many galaxies would be found at specific redshifts, at specific luminosities, in specific survey areas became the benchmarks against which Webb's actual findings were measured. When Rohan Naidu's team reported that the number density of galaxies at redshifts between 14 and 15 was more than 180 times higher than the theoretical consensus, those are Techella and Robertson's models that the 180 times refers to. The models are published. The predictions are on the record. The discrepancy is not abstract. It is specific. It is quantified. And it belongs to specific people who are now working to understand what their models missed. This is what the sensationalist version of this story, The Big Bang is broken, the standard model is dead, everything we knew was wrong, completely misrepresents. The researchers whose predictions failed are not discredited. They are not defending a mistake. They are doing what scientists do when the data contradicts the model. They are going back into the assumptions and looking for what was incomplete. That process is ongoing, and it is serious, and the people doing it are the same people who built the original models. Techella himself is a co-author on multiple Webb papers. Robertson is a core member of the JADES collaboration that confirmed JADES GS-Z14O. The people whose models are being contradicted are the people doing the follow-up observations. That is how the field actually works. It is less dramatic than a paradigm collapse, and more interesting, because it means the failure is being interrogated from the inside by the people who understand it best. What the models most consistently failed to anticipate was efficiency. In a typical galaxy in the local universe, the conversion of gas into stars is extraordinarily inefficient. The Milky Way today produces between 2 and 6 new stars per year. It has been doing this for most of its history. The star formation efficiency, the fraction of available gas that actually gets converted into stars, rather than being blown back out by supernova feedback or stellar winds or active galactic nuclei, is somewhere between 1 and 3%. The rest of the gas stays gas, or gets heated and ejected, or slowly cycles through and tries again over billions of years. This inefficiency is not a failure of the Milky Way. It is a feature. If it had converted all its gas into stars rapidly, it would have run dry long ago, and there would be no new stars forming today. The inefficiency is the engine of the galaxy's longevity. The early galaxies that Webb keeps finding apparently operated on a completely different principle. The theoretical models that tried to reproduce galaxies with the stellar masses Lab and others were measuring required star formation efficiencies approaching 100% in some cases, all the gas turning into stars. Almost immediately, with no delay. At near 100% efficiency, there is no time for supernova feedback to slow the process down. There is no time for stellar winds to sweep gas out of the star-forming regions. There is no time for the galaxy to regulate itself through any of the feedback mechanisms that galaxy formation models had assumed were universal features of how galaxies grow. The early galaxies were not following the rulebook. The question was whether the rulebook was wrong, or whether something else was happening that the rulebook had not anticipated. 3 explanations emerged from the community, and watching those explanations develop, watching the people who hold them argue for them in conference rooms and in papers and in the hallways of telescope facilities, is where the human texture of this story lives. Caitlin Casey is an astrophysicist at the University of Texas at Austin, who has spent her career studying galaxy formation and evolution. She led one of the largest Webb survey programs in the first year of operations, and she has been in the middle of the theoretical debate since it began. When she talks about the initial mass function, the distribution of masses among newly formed stars, she does not use cautious language. She says it plainly: the initial mass function is the house of cards on which we build everything. And there are many reasons to believe it is quite different at very high redshift. The initial mass function matters because it determines how bright a galaxy appears relative to how massive it is. Stars form across a range of masses, from a fraction of the Sun's mass to dozens or hundreds of times the Sun's mass. And the distribution of that range, how many small stars form for every large one, sets the ratio of a galaxy's luminosity to its stellar mass. In the local universe, that ratio is well measured. It is one of the fundamental constants of galaxy formation theory. Every simulation, every model, every prediction of how bright a galaxy should be at a given stellar mass is built on the assumption that this ratio, while not perfectly uniform, is approximately consistent across cosmic time. If the early universe produced a different distribution of stellar masses weighted toward more massive, hotter, brighter stars, then every early galaxy would be intrinsically more luminous per unit of stellar mass than the models assumed. The galaxies would not be more massive than expected. They would be brighter per unit of mass than expected, and the models, which assumed a local mass-to-light ratio, would systematically overestimate the stellar masses derived from the brightness of early galaxies. The problem would not be that too many stars formed too fast. The problem would be that each star was burning brighter than the model said a star of that mass should burn, and the model was translating that excess brightness into excess mass. Casey's position that the initial mass function was genuinely different in the early universe is not a fringe argument. It is supported by the chemical evidence coming out of Webb spectra. The unusual nitrogen enrichment in galaxies like MOM-Z14 and GN-Z11 is most naturally explained by stars with masses between 1,000 and 10,000 solar masses objects that do not exist in the local universe. That would have burned through their fuel in 2 million years and died in explosions that produced specific chemical signatures distinct from ordinary supernova nucleosynthesis. If those stars existed in the early universe, they would have changed everything about how the first galaxies appeared: their brightness, their chemistry, their capacity to ionize the surrounding hydrogen. They would be the engine of the early universe's apparent overproduction, and their chemical fingerprints are exactly what Webb spectra are finding. But there are problems with this explanation that Casey and others are the first to acknowledge. A top-heavy initial mass function 1 weighted toward very massive stars creates specific predictions about dust production, about chemical enrichment rates, about the timing and intensity of supernova feedback. Some of those predictions are consistent with what Webb is finding. Others create new tensions. If the first stars were predominantly massive, their deaths would have produced large amounts of heavy elements very rapidly, which is consistent with the oxygen and nitrogen detections in early galaxies. But those deaths would also have produced large amounts of dust, and some early galaxies appear surprisingly dust-free, which complicates the picture. The second explanation belongs primarily to Julian Muoz, whose reionization paper we have already met, and to researchers like Pratica Dayal at the University of Groningen in the Netherlands. It is about burstiness, the idea that the early universe was not more efficient at forming stars on average, but that it formed them in violent, concentrated episodes that made individual galaxies temporarily much brighter than their long-term average. In this picture, the early universe was characterized by extreme variability. A galaxy would go through a period of furious star formation triggered by a merger, by an influx of cold gas, by some instability in the dense early cosmic environment during which it would shine 100 times brighter than its quiescent average. Then the supernova explosions from that burst of star formation would blow gas out of the galaxy, starving the star-forming regions and dimming the galaxy back down. Then the gas would fall back in, trigger another burst, and the cycle would repeat. If Webb is preferentially catching these galaxies during their bright phases, which selection effects would naturally cause, since you can only detect what is bright enough to see, then the sample of confirmed early galaxies would be biased toward the exceptional moments, rather than the typical ones. Burstiness does not require changing the physics of star formation. It does not require a different initial mass function or exotic early stellar populations. It requires only that the early universe was lumpier, more turbulent, more concentrated in its star-forming activity, than the relatively smooth, continuous star formation that characterizes mature galaxies like the Milky Way today. This is plausible. The early universe was denser. Galaxies were smaller. Gas fractions were higher. Mergers were more frequent. All of these factors favor violent, episodic star formation over the steady, regulated kind. The challenge for the burstiness explanation is that it works better for some galaxies than others. For the most extreme cases, galaxies with implied stellar masses of 100 billion solar masses at redshifts above 10 burstiness alone does not close the gap between the observations and the models. Even if you assume the galaxy was caught at the peak of its brightest burst, the implied average star formation rate over its lifetime is still higher than the models comfortably accommodate. Burstiness reduces the problem. For the most extreme objects, it does not solve it. Andrea Ferrara at the Scuola Normale Superiore in Pisa has been developing the third explanation for several years, and he presented a version of it at the Kavli Institute for Theoretical Physics in Santa Barbara in the summer of 2024. His argument is about dust, specifically about how much dust the early galaxies had, and how the absence of dust changes how bright they appear. Dust is the enemy of ultraviolet light. In galaxies like the Milky Way, dust absorbs a substantial fraction of the ultraviolet radiation produced by young hot stars and re-radiates it at infrared wavelengths. This means that when you observe a galaxy in ultraviolet light, you are seeing only the fraction of the total ultraviolet production that escaped without being absorbed. The correction for dust absorption, the dust attenuation, is one of the largest sources of uncertainty in measuring the true star formation rates and stellar masses of galaxies. Get the dust wrong, and you get the galaxy wrong. Ferrara's argument is that the first galaxies had radically less dust than their later counterparts, not because they had not produced the raw materials for dust, but because the intense radiation pressure and supernova-driven winds of the first stellar generations swept the dust out of the galaxies before it could accumulate in the star-forming regions. If early galaxies were nearly dust-free, then the ultraviolet light from their young stars was escaping with almost no attenuation, and the galaxies would appear far brighter in ultraviolet surveys than a model calibrated on dusty local galaxies would predict. The excess brightness would be real, but it would reflect the transparency of the early galaxies, not an excess of stars. Ferrara presented the model and then said something that was both honest and funny, so please don't discover other galaxies. The room laughed. What he meant was that his model works for the redshift ranges where it has been calibrated, but that pushing the observations further to redshifts of 14 or above, to galaxies like MOM-Z14, stretches the model beyond where it has been tested. And he did not know yet whether it would hold. That admission, made in front of 100 colleagues, is the texture of how science actually works, not pronouncements from authority, but calculations presented to a room full of people looking for the holes. The three explanations are not mutually exclusive. Ferrara himself is open to all three being partially true: a different initial mass function, contributing some of the excess brightness, burstiness contributing some, reduced dust contributing the rest. Most researchers in the field hold their preferred explanation loosely and watch the new data for the signal that will distinguish between them. What distinguishes this from ordinary scientific uncertainty is the scale of the gap that needs explaining. When a model is off by 10 or 20%, you look for calibration issues. When it is off by a factor of 180, you look for something you missed in the physics. Kevin Hainline was at the University of Arizona in January 2023, working through imaging data from the JADES program, the James Webb Space Telescope Advanced Deep Extragalactic Survey, one of the largest dedicated observing programs on the telescope, a collaboration between the NIRCam and NIRSpec instrument teams that had been planned for years before Webb launched. His job that day was the same kind of pipeline work Lab had been doing 6 months earlier, feeding data through software, looking at what came out, cataloging candidates. He was looking at a patch of sky in the constellation Fornax, one of the deep fields that previous telescopes had stared at for hundreds of hours, one of the most studied pieces of sky in astronomy. He found something in the data that stopped him. He stood up from his chair. He did not know yet what it was. He knew it was a candidate, an object at what the photometric redshift estimated to be an extraordinary distance, sitting at a redshift that would place it in the first 300 million years of cosmic history. He had found hundreds of candidates over the course of his work on jades. Candidates are not confirmation, but this one was different in a way he could not immediately articulate. It was too bright for where it appeared to be. Not a little too bright. Conspicuously, troublingly too bright. Too bright for the models. Too bright for the predictions. Too bright for what any theoretical framework said should be visible at that distance and that epoch. He labeled it Jade's GS-Z14-0, with the dry systematic naming convention that science uses when it has not yet decided what something is. The follow-up took more than a year. In January 2024, the JADES team pointed Webb's NIRSPEC instrument at JADES GS-Z14-0 and observed it for almost 10 hours. 10 hours of a telescope that costs $10 billion and is in finite supply, pointed at a single fuzzy smear of light in Fornax, collecting photons that had been traveling for the better part of the universe's entire history. When the spectrum came back, it confirmed what the imaging had suggested. The galaxy had a redshift of 14.32, placing its light at 290 million years after the Big Bang. It was the most distant object ever confirmed by spectroscopy. It was also, at that distance, enormous 1,600 light-years across, blazing with ultraviolet radiation, producing stars at a rate that the model said was implausible at that epoch. And it had oxygen. Oxygen should not be there. Not at 290 million years after the Big Bang. Not in a galaxy at that distance and that epoch. Oxygen is not a primordial. The universe began with hydrogen and helium and trace amounts of lithium. Everything heavier than that, every carbon atom, every nitrogen atom, every oxygen atom was forged inside stars and released into the surrounding gas when those stars died, either in the slow exhalation of a stellar wind or in the catastrophic detonation of a supernova. This process takes time. The first stars had to form. Then they had to live out their stellar lives tens of millions of years for the most massive ones. Then they had to die and scatter their nuclear products through the galaxy. Then a second generation of stars had to form from the enriched gas. Oxygen in a galaxy's spectrum is a record of that entire process having occurred, of stars having lived and died, and given the galaxy the chemical complexity it needed to produce oxygen in detectable quantities. JADES GS-Z14-0 existed 290 million years after the Big Bang. The universe at that point was 2% of its current age. And it had oxygen. Sander Schaus is a PhD candidate at Leiden Observatory in the Netherlands. He is not a senior figure in the field. He is a graduate student doing the careful, detailed work that graduate students do, processing data, checking calibrations, writing the sections of papers that will eventually carry someone else's name higher on the author list. He was part of one of two independent teams that detected the oxygen in JADES GS-Z14-0 using the Atacama Large Millimeter Submillimeter Array in Chile, a network of 66 radio antennas spread across the Atacama Desert at an altitude of 5,000 meters above sea level. ALMA observes at millimeter and submillimeter wavelengths the wavelengths at which oxygen's characteristic emission line appears when it is redshifted from a galaxy at redshift 14. Finding that signal in the noise, at that distance, from an object that occupies a fraction of a square arcsecond on the sky, required exactly the kind of painstaking observational work that Schaus and his collaborators did. He described the finding by saying it was like finding an adolescent where you would only expect babies. That is not a colorful metaphor chosen for public communication. It is a precise description of the conceptual problem. A galaxy 290 million years old, in a universe that is only 2% of its current age, should be chemically primitive. It should look like a newborn made mostly of the hydrogen and helium the Big Bang produced, with the barest trace of heavier elements from the first generation of stars. Finding oxygen in abundance is finding evidence that the galaxy has already gone through the full cycle of stellar birth and death and chemical enrichment that was supposed to take far longer. It is finding the adolescent where the physics says only the newborn should exist. Stefano Carniani at the Scuola Normale Superiore in Pisa led the second independent team that confirmed the oxygen detection. He said he was astonished not by the galaxy's existence, because by early 2025 the existence of bright early galaxies had become something the community was learning to live with, but by the chemical maturity implied by the oxygen. The evidence that a galaxy is already mature in the infant universe raises questions, he said, about when and how galaxies formed. 10 times more heavy elements than expected. That is what the oxygen detection implied, that Jade's GS-Z140 had enriched itself to roughly 10 times the metallicity that anyone would have predicted for a galaxy at that age. For that to happen, multiple generations of stars had to have lived and died inside it. Multiple generations. In 290 million years. In a universe that was still mostly hydrogen fog. Eleonora Parlanti is a PhD student at the Scuola Normale Superiore in Pisa, working under Carniani. She noted something about the oxygen detection that received less attention than the detection itself, but that matters as much. The ALMA measurement pinned the galaxy's distance to an uncertainty of 0.005% accurate, she said, to within 5 centimeters over a distance of 1 kilometer. That level of precision does something specific. It closes off the last escape route the skeptical mind reaches for. Maybe the distance is wrong. Maybe the photometric estimate was off. Maybe the galaxy is not as far away as it looks. It is exactly as far away as it looks. The oxygen spectrum confirmed it to 5 significant figures. The galaxy is real. Its age is real. Its chemistry is real. The problem it represents is real. Richard Bowens is an associate professor at Leiden Observatory, a senior figure in the field who has spent decades studying galaxy populations at high redshift, and who was a team member on the ALMA detection. He put the significance of the oxygen finding in terms that connected the two instruments rather than treating them separately. While the galaxy was originally discovered with Webb, he said, it took ALMA to confirm and precisely determine its enormous distance. The synergy between ALMA and Webb, one seeing the light of the stars, the other hearing the chemical signature of what those stars left behind, is what made the oxygen detection possible. And what that synergy revealed was a galaxy that had no business being as chemically mature as it was. Jade's GS-Z140 held the distance record for about a year. Then came MOM Z14. The name comes from the survey that found it mirage or miracle. Rohan Naidu is a Pappalardo Fellow at MIT's Kavli Institute for Astrophysics and Space Research at 70 Vassar Street in Cambridge, Massachusetts. The Pappalardo Fellowship is one of the most competitive postdoctoral fellowships in physics. It selects 3 fellows per year from the entire field, across all subfields of physics, and gives them complete independence to pursue whatever research they consider most important. Naidu chose the early universe. Specifically, he chose the question that had been sitting at the center of the field since Lab's coffee cup trembled in July 2022, whether the extreme brightness of the galaxies Webb was finding was a mirage or a miracle. He designed the MOM survey with Pascal Oesch at the University of Geneva. Oesch is a NASA Hubble Fellow and one of the leading observers of the high redshift universe. A researcher whose career has been built on pushing the observational frontier further back in time with each new instrument generation. Together they designed GWEST Program 5224, a systematic spectroscopic survey of luminous galaxy candidates at photometric redshifts above 10, spread across the cosmos and UD's legacy fields. Structured to answer the mirage or miracle question with enough statistical power to be definitive rather than suggestive. The cosmos field is a large legacy survey region in the constellation Sextans, one of the most intensively observed patches of sky in astronomy, covered by data from essentially every major telescope and space observatory of the last 2 decades. The UD's The Ultra Deep Survey is its counterpart in the constellation Cetus. Together they give the MOM survey the wide area coverage needed to find rare objects like MOM Z14 without the bias introduced by targeting already known structures or overdensities. On May 16, 2025, the NIRCam instrument aboard Webb imaged a source in the cosmos field at coordinates that would have meant nothing to anyone without the catalog right ascension 10 hours, 0 minutes, 22.4 seconds, declination 2 degrees, 16 arc minutes, 23.19 arc seconds in the constellation Sextans. The source was compact, barely resolved, absent at wavelengths shorter than 2 microns, which is the signature of a galaxy so distant that its ultraviolet light has been redshifted entirely out of the visible range by the expansion of the universe over 13.5 billion years of travel. The near-spec spectrograph observed it for 4.4 hours. The spectrum came back showing a sharp Lyman alpha break, the sudden cutoff of light at the wavelength, where neutral hydrogen absorbs photons, the cleanest possible signature of a very distant galaxy, along with detections of 5 ultraviolet emission lines. The redshift, 14.44, plus or minus 0.02, 280 million years after the Big Bang. A new record. Further than Jade's GS-Z14-0 by 10 million years, pushed back another step toward the moment when the first light in the universe ignited, when the first stars tore their way into existence out of the primordial hydrogen, and began the work of making the cosmos chemically complex enough to eventually produce the telescopes that would find them. Naidu's immediate response to the finding was characteristic. He did not say it was the most distant galaxy ever found. He said, "It looks nothing like what we predicted," which is both challenging and exciting. His postdoctoral colleague Jacob Shen was more precise in his language. "There is a growing chasm between theory and observation related to the early universe," Shen said. A growing chasm, not a tension, not a discrepancy. A chasm, a word that implies not just distance between two positions, but the impossibility of crossing it without something fundamental changing on one side or the other. The number density of objects like MOM Z14 is where the chasm is most quantifiable. The pre-Webb consensus models the best theoretical predictions of galaxy abundance at redshifts between 14 and 15. Built by Takela and Robertson and their collaborators using the most sophisticated simulations available before Webb launched, predicted that such objects would be extraordinarily rare. The survey area of the MOM program, approximately 350 square arc minutes, was not expected to contain any confirmed galaxies at those redshifts and luminosities. It found one. The implied number density is 182 times higher than the theoretical consensus predicted. The error bars on that figure are large. The discovery paper cites a range from 77 times to 511 times higher, reflecting the statistical uncertainty of a single detection in a finite survey area. But even the lower bound of that range, 77 times, represents a failure of prediction so complete that it cannot be attributed to noise or calibration or bad luck. Something in the models is missing, something that matters at the order of magnitude level. MOM Z14 had nitrogen. Not just nitrogen present in trace amounts an unusual abundance pattern in which the ratio of nitrogen to carbon was highly elevated above solar values, and in which the ratio of nitrogen to oxygen was elevated in a way that is essentially impossible to produce through ordinary stellar nucleosynthesis on ordinary timescales. The same pattern had been seen in GN-Z11, the galaxy that Hubble first identified at high redshift and that Webb subsequently confirmed and characterized in precise spectroscopic detail. The same pattern appears in the spectra of the oldest stars in the Milky Way's globular clusters, the dense, ancient stellar systems that orbit the galaxy and that contain stars formed in the earliest epochs of the Milky Way's history. Stars that are themselves relics of the cosmic dawn, stars that are 13 billion years old and still burning slowly enough to observe in detail with modern instruments. Naidu described the connection in language that was careful but that pointed toward something large. "We can take a page from archaeology," he said, "and look at these ancient stars in our own galaxy like fossils from the early universe. We are seeing some of the same features like this unusual nitrogen enrichment." What he was describing is a thread that runs from the most distant galaxy ever confirmed 280 million years after the Big Bang, 13.5 billion light-years away, to the oldest stars in our own galaxy, close enough to observe with ground-based telescopes from a mountaintop in Chile or Hawaii. The same chemical signature, the same fingerprint, as though the stars in the Milky Way's ancient globular clusters and the stars in MOM Z14 were shaped by the same physics, in the same early environment, before the universe had been anything other than hydrogen and helium and the first chaotic structures of the cosmic dawn. The theory for how the nitrogen got there requires something that does not exist in the universe today. Supermassive stars, objects with masses between 1,000 and 10,000 times the mass of our Sun, stars so enormous that they occupy a regime of physics that has never been directly observed, where gravity and radiation pressure compete so intensely that the stars are gravitationally unstable by any standard model of stellar structure, where the nuclear burning rates are so extreme that the stellar lifetime is measured in a few million years rather than billions, where the nucleosynthesis produces specific chemical signatures that differ from ordinary supernova products in ways that match exactly the nitrogen to carbon and nitrogen to oxygen ratios that Webb keeps finding in the most distant galaxies. These stars, if they existed, would have left no directly observable remnant. They would have lived fast and died completely, their mass dispersed into the surrounding gas, their chemical products incorporated into the next generation of stars. The evidence for their existence is entirely indirect. It is the pattern of abundances they left behind, read out of the spectra of galaxies that formed when the universe was 2 or 3% of its current age, and read out of the spectra of ancient stars in the Milky Way that are themselves the descendants of those early galaxies. The supermassive stars are gone, their fingerprints are not. The Santa Barbara Conference in August of 2024 was where the field took stock of where it stood, 2 years into the Webb era. The Kavli Institute for Theoretical Physics hosts extended programs visiting scholars live in apartments provided by the institute, share meals and evening walks along the California coast, and spend weeks or months working through problems together in a way that the normal rhythm of conferences and grant cycles does not allow. About 100 astrophysicists came for the program on the early universe, and what happened over those weeks was not a conference in the ordinary sense, not a sequence of prepared talks delivered to passive audiences. It was a community working through a shared surprise in real time, and the texture of that working through is different from what appears in the published papers. Kevin Heinlein was there. He had been living with the JADES data for a year and a half at that point, and he had been in the middle of the field's internal debate about what the data meant and how to talk about it. He was asked by a reporter whether the findings were as revolutionary as they seemed from the outside. He said, "We are knocking on the door of history." Then he said something that illuminated the field's internal experience more precisely. "Astronomers need to be better about celebrating discoveries." That sentence carries more information than it appears to. It is an acknowledgement that the field had spent much of the first 2 years of Webb data in a defensive crouch, careful not to overclaim, careful to distinguish between what the observations showed and what the press wanted them to show, careful to say unexpected and challenging rather than impossible and revolutionary. The caution was scientifically appropriate. It was also, Heinlein was suggesting, costing the field something. What it was costing was the full recognition of what was actually happening. Something genuinely unprecedented was unfolding. A telescope was seeing the early universe for the first time, and what it was seeing was contradicting the predictions of the field's best models, not at the margins, but at the center. This is not what normally happens in mature science. Mature science produces incremental improvements, refinements of existing frameworks, confirmation of predictions with greater precision. What Webb was producing was not refinement. It was contradiction at the order of magnitude level, repeatedly, from multiple independent teams using multiple instruments across multiple observing programs. And the field was describing this, publicly, in the language of tension and discrepancy and unexpected results. Because that is the appropriate scientific language, and because the appropriate scientific language is calibrated for an audience of professionals who know what tension and discrepancy mean. The popular press did not know what tension and discrepancy mean. The popular press heard tension and discrepancy and translated it into Big Bang broken, Standard Model dead. Everything we knew was wrong. And the scientists, watching that translation happen, became more cautious, which produced more measured language, which produced more sensationalist interpretation, which produced more caution, in a cycle that was making everyone less happy without making anyone more accurate. Alice Shapley at UCLA is one of the leading spectroscopists of the high redshift universe. She has been working on the chemical properties of early galaxies for more than 2 decades, and she was at the Santa Barbara conference. She said there was a lot of sensationalism in JWST's early days. There is no need for that. The data are so beautiful, let's just study the universe we have. That last sentence, let's just study the universe we have, is not a retreat from ambition. It is a reorientation of ambition. It is the field deciding, together, to stop performing revolution and start doing the harder and more interesting work of understanding what the data actually contains. The universe Webb is revealing is stranger and more complex than the models predicted. That strangeness does not need to be dressed up in broken Big Bang language to be significant. It is significant on its own terms. The early universe was more productive, more chemically complex, more luminous, and more structured than anyone expected. Understanding why requires building better models, not abandoning the ones that failed. Andrei Kravtsov is a cosmologist and theoretical astrophysicist at the University of Chicago, who also spent part of that summer at the Kavli Institute. He is primarily a theorist, someone who builds models and simulations of galaxy formation, rather than someone who takes data from telescopes, and he told a reporter that the little red dots were the biggest discovery of JWST so far. The little red dots are a new class of objects that Webb began finding in the early universe, small, red, compact sources that appeared in the first years of Webb data, and that have no clear counterpart in the local universe. They are not the massive early galaxies that Lab found. They are something else entirely, and Kravtsov was struck by how the discovery felt similar to the discovery of quasars in the 1950s and 60s, objects that appeared in the data and that nobody had a framework for. That generated years of competing theories before the community coalesced around the understanding that they were supermassive black holes accreting material at extreme rates. The little red dots might be something similar. The gas in them appears to be moving at extraordinary speeds, 3,000 kilometers per hour, compared to the 300 kilometers per hour typical of gas being flung around by stellar feedback in ordinary galaxies. Only something very massive can accelerate gas to those speeds. Some researchers argue the little red dots contain spinning supermassive black holes. Erica Nelson, who sent Lab the message that started all of this in July 2022, has proposed an alternative, that the little red dots are not dominated by black holes, but are instead extremely compact balls of densely packed gas and stars, so dense that the internal motions of the gas produce the high velocities that look, from a distance, like black hole signatures. The two explanations are not yet distinguishable with current data. They require the deeper spectroscopy that only the next generation of instruments can provide. Kravtsov described the situation with a kind of professional pleasure, the pleasure of a theorist who has been handed a genuine puzzle with no obvious solution. In a few years it will be figured out, he said. But right now it's exciting to be in this process of discovery. That sentence is the honest account of what the Santa Barbara conference felt like from the inside, not a crisis, not a revolution, but the specific intellectual excitement of a field that has been handed more good questions than it has time to answer. Seiji Fujimoto at UT Austin presented work during the conference that illustrated one of the more unexpected findings of the Webb era. He had been studying a bright galaxy that Webb imaged, as it appeared 930 million years after the Big Bang, not as distant as the record holders, but close enough to the cosmic dawn to be of intense interest. Using gravitational lensing, the bending of light around a massive foreground object that acts as a natural telescope, magnifying whatever lies behind it, Fujimoto was able to see the galaxy's structure in detail that direct imaging could not provide. What he found was that the galaxy was not one object. It was a cluster of at least 15 individual star-forming clumps, packed together. Each one a dense knot of gas and young stars, the whole assembly resembling a bunch of grapes, rather than anything like the smooth, disc-shaped galaxies familiar from the local universe. The grape cluster structure caused a stir in the conference that lasted for days. Rachel Somerville, a theoretical astrophysicist at the Simons Foundation who had co-organized the meeting, wondered aloud whether all high redshift galaxies might be made of dense clumps like Fujimoto's grapes, whether the smooth galaxy appearance of earlier observations was a resolution effect, and that underneath every one of those seemingly smooth early galaxies was a complex, clumpy assembly of star-forming regions. Dense clumps could produce stars with extreme efficiency, she noted. Dense clumps could shine brightly for their mass. Dense clumps could explain the apparent overabundance of luminous early galaxies without requiring exotic stellar populations or physically implausible star formation rates. "We need to think about this harder," she said, a phrase that came to characterize the gathering spirit. Viraj Pandya at Columbia University added another layer of strangeness to the picture. He had been studying early galaxies that were not round, not disc-shaped, not anything that fit the standard classification schemes. They were elongated, stretched into shapes like cigars or pickles, with stars arranged along a single axis rather than distributed across a disk or a sphere. Pandya described them as galaxies going bananas. This new class of early elongated galaxies has no clear counterpart in the local universe. They appear to have been a feature of the cosmic dawn and then to have disappeared, transformed into the more familiar shapes that constitute the galaxies we see today. What turned a banana-shaped early galaxy into a modern elliptical or spiral is another of the questions that Webb has opened without yet answering. The picture that emerged from Santa Barbara was not one of consensus or resolution. It was one of multiplying strangeness, a growing catalog of early universe objects and phenomena that do not fit the existing frameworks, that do not obviously fit each other, that collectively suggest the first billion years of cosmic history was doing things that the local universe gave no clear indication of. Kevin Hainline, in his most candid moment of the conference, put it simply. People were saying, "Well, it can't be that," and the observers are like, "This is what we see," and then theorists can go figure it out and mess around. That is not the language of a field in crisis. It is the language of a field that has just been handed a telescope powerful enough to outrun its theories, and is working with some urgency and considerable excitement to catch up. What the early universe was actually doing is the question that MOM Z14 pushed forward in May 2025. The galaxy is 240 light-years across a dwarf galaxy by modern standards, smaller than the Large Magellanic Cloud, the satellite galaxy that orbits the Milky Way at a distance of 160,000 light-years, and is visible to the naked eye from the southern hemisphere. At the time we observe it, 280 million years after the Big Bang, MOM Z14 had already been through at least one intense burst of star formation. The emission lines in its spectrum show a star formation rate that had increased by a factor of 10 in the last 5 million years before the moment its light left it. It was clearing the hydrogen fog in its immediate surroundings, creating a bubble of ionized gas around itself in a universe that was otherwise still almost entirely neutral. It was, in that sense, one of the early agents of reionization, one of the first objects to begin the work that would eventually clear the primordial fog and make the cosmos transparent. One of the galaxies whose ultraviolet radiation was contributing to the accounting that MUOS would later do, the accounting that showed reionization must have ended earlier than the cosmic microwave background says it should have, because there were more of these galaxies, burning brighter than anyone had predicted. that Mom Z14 was doing this 280 million years after the Big Bang, when the models said there should be essentially nothing bright enough to observe at that distance. When the pre-Webb consensus predicted that even finding a single faint galaxy at that epoch would require hundreds of hours of telescope time as the finding. Not a finding about one galaxy. A finding about what the early universe was capable of. A finding that the first structures to form in the cosmos were more vigorous, more chemically sophisticated, and more numerous than the framework built on the oldest light had given us reason to expect. The survey that found Mom Z14 was named for a question: mirage or miracle? After the result, the question has not been answered. It has been sharpened. The galaxy is not a mirage. The spectroscopy is unambiguous. The redshift is confirmed to 2 decimal places. The emission lines are real. The nitrogen abundance pattern is real. The ionized bubble surrounding it is real. What it is a miracle of what physics in the early universe permitted a galaxy to exist at 280 million years with the properties Mom Z14 has, is what the field is now working to understand. The cosmic microwave background says reionization ended around 1 billion years after the Big Bang. The galaxy's Webb's findings say it ended between 550 and 650 million years after the Big Bang. Both measurements emerge from careful, validated, peer-reviewed science. Both are calibrated against data taken with instruments that have been extensively characterized. The uncertainty in the CMB measurement is small. The Planck collaboration spent years reducing it. The uncertainty in the Webb galaxy counts is larger, because the samples are still small and the selection effects are still being characterized. But it is not large enough to close a gap of 350 million years. Something is missing from one side of the equation. Perhaps the recombination rate in the CMB calculation, the rate at which ionized hydrogen recombines back into neutral hydrogen, is slightly higher than current models assume, which would require more ultraviolet radiation to complete reionization, and would push the end of reionization later, closer to the CMB's billion-year estimate. Perhaps the Webb galaxy samples are still missing a significant population of faint galaxies that contribute substantially to the ionizing photon budget, but that are too dim to be confirmed spectroscopically with current exposure times. Perhaps both are partially true. Perhaps there is something else entirely, some physics in the epoch of reionization that neither the CMB calculation nor the galaxy census has yet captured. Muoz himself leans toward the recombination explanation as the most promising avenue for reconciliation. The argument is that clumping of the gas in the early universe, the degree to which hydrogen was concentrated in dense filaments and voids, rather than distributed uniformly, directly affects how frequently ionized protons and electrons recombine back into neutral hydrogen. More clumping means more recombination, means more ultraviolet photons needed to maintain the ionized state, means the end of reionization is pushed later. If the early universe was clumpier than the models assume, and the Fujimoto grape cluster discovery suggests it might have been, since dense clumps represent extreme local concentrations of matter, then the CMB and Webb measurements might be reconcilable without requiring either one to be wrong at a fundamental level. It is, as Muoz says, an accounting problem. The ledger has 2 sides. The CMB is one and Webb's galaxy counts are another. They do not yet balance. Finding the missing term, the physics that makes them balance, is the next chapter of this story. And it will be written over the next decade, in a sequence of observations and papers and conferences that will look, from the outside, like the normal operation of science, and that will feel, from the inside, like the work of people who have been handed a genuine mystery and are not sure yet what shape the answer will take. Rohan Naidu is still working on the MOM survey data. The full census, all 5 NIRSPEC pointings in the cosmos and UDS fields, every targeted galaxy, every confirmed and rejected candidate. The complete accounting of what was there and what was not is in preparation as a subsequent paper. The results will give the number density measurement a statistical foundation broader than the single detection of MOM Z14. They will show whether MOM Z14 was itself a fluke within a milder overabundance, or whether it was representative of a population that is genuinely as extreme as the 182 times higher than predicted figure implies. That answer will shape the theoretical response, will tell the model builders how far they need to reach, and in which direction, and whether the fixes that Casey and Ferrara and Muoz and Dial have been working on are sufficient, or whether something more fundamental needs to change. Ijia Lee is a graduate student at Penn State who is part of the MOM Z14 discovery team. She said something at the end of the discovery paper that is easy to pass over and should not be. She said, "It's an incredibly exciting time, with Webb revealing the early universe like never before, and showing us how much there still is to discover." That sentence is written by someone who has spent years working toward a specific answer, and has found, instead of the answer, a better version of the question. That is not disappointment. That is the experience of science working correctly, the discovery that the universe is more interesting than the framework you brought to it. Lab's arc from July 2022 to the present has the quality of a question that expanded rather than contracted as it was investigated. He found 6 impossible objects in the first week of Webb data. The spectroscopy confirmed some and eliminated others. The confirmed ones turned out to be chemically mature in ways that deepened the impossibility rather than resolving it. New surveys found more of them, further away, earlier in the universe's history, with the same unexpected properties repeated across independent observations by independent teams using independent instruments. The oxygen kept appearing where the models said it had no time to form. The nitrogen kept appearing with the same elevated ratio that shows up in the most ancient stellar populations in our own galaxy. Each new confirmed galaxy was another point on a curve that was not bending back toward the theoretical prediction. It was pulling away from it. The thread connects across 13.5 billion years. From the oldest stars in the Milky Way's globular clusters, stars that formed in the first billion years of the galaxy's history, stars that still burn slowly enough to be observed in detail from Earth, stars whose spectra show the same unusual nitrogen signature that Webb is finding in the most distant galaxies, to MOM Z14 itself, a galaxy that existed when the universe was 2% of its current age, and that carries in its spectrum the same chemical fingerprint. The stars in the ancient globular clusters may be the literal descendants of galaxies like MOM Z14. They may have formed in systems like it, in that same early epoch, and been incorporated into the Milky Way through billions of years of mergers and accretion, carrying their chemical signature through all that time and all that transformation, until they arrived here, in our galaxy, close enough to study with instruments we built on a planet that did not exist until 9 billion years after they were born. This connection between the nearest ancient stars and the most distant known galaxies is the finding that almost every popular treatment of this story has missed. The usual version focuses on the distance record, on the spectroscopic confirmation, on the headline number of how many million years after the Big Bang. Those are real. But the deeper finding is the chemical continuity, the evidence that what happened in the first 300 million years of cosmic history left marks that are still readable 13 billion years later, in our own stellar neighborhood, in stars that are old enough to remember the cosmic dawn even if they formed long after it. Webb is not just showing us distant galaxies. It is showing us the origin of the oldest things in our own galaxy, and the connection between what we can see nearby and what we can barely reach with the most powerful telescope ever built is the thread that makes this story about more than distance records. Evo Lab wrote that he nearly spilled his coffee. He nearly spilled it because the number that appeared on his screen, 100 billion solar masses, 13 billion light years, together in the same object, together in the first billion years of cosmic time, should not have been there. The framework he had spent his career building and refining and trusting told him it should not be there. The framework was wrong. Not catastrophically wrong. Not wrong in the way that requires abandoning everything and starting over from a blank page. Wrong in the specific instructive way that means the framework was built without a complete picture, and now the picture is becoming more complete, and the framework has to grow to fit what the picture is showing. The cosmic microwave background is still the oldest light. It is still the most precise measurement of the early universe's initial conditions. It is still the bedrock against which every other cosmological measurement is calibrated. Webb has not replaced it. What Webb has done is push the observations into the epoch between the oldest light and the first galaxies into the Dark Ages, into the reionization epoch, into the period that the CMB illuminates only indirectly, through the statistical fingerprints it leaves in the polarization and temperature patterns of 13 billion-year-old photons. Webb sees what came just after the first objects that tore through the neutral hydrogen fog, the first galaxies that tore holes in the primordial darkness and let light travel. And what it sees is that those objects were doing it faster, and more vigorously and with more chemical sophistication than the oldest light gave us reason to expect. The timeline did not break. It was always this shape. The universe has always been this efficient, this productive, this chemically complex in its first 300 million years. We simply did not have a telescope that could show us. We had the CMB, which is the light from before any of it happened, and we had theoretical models built on the assumption that the local universe was a sufficient guide to the early one, and we had Hubble, which could see back 1 billion years past its own engineering limit, but not into the cosmic dawn itself. We had, in other words, everything except direct observation of the thing we were trying to understand. And in the absence of direct observation, we built frameworks. And the frameworks were good, and they were calibrated against the best available indirect evidence. And they were wrong in ways that only direct observation could have revealed. Webb is the direct observation. What it is showing us is that the universe in its earliest epoch was already doing what the universe does, building structure, making stars, enriching gas with heavy elements, clearing the hydrogen fog at a rate and with a vigor that exceeds what the models calibrated against the oldest light had room for. The models needed updating. The updating is underway. The people doing it are the same people who built the original models, and they are doing it with the same careful attention to what the data actually says rather than what the narrative wants it to say. It will take years. The answer will come in pieces: a better constraint on the recombination rate here, a deeper census of faint early galaxies there, a spectrum of an ancient globular cluster star that pins down the nitrogen abundance to a precision that closes the gap between the nearby and the distant, and the full picture will emerge incrementally, the way all pictures in science emerge, through accumulation rather than revelation. In the meantime, in a small room at 70 Vassar Street in Cambridge, Rohan Naidu is working on the data. The full MOM survey results are in preparation. Somewhere in the cosmos field, at coordinates that will eventually be in every textbook that covers this period, there is a galaxy that existed when the universe was 280 million years old, and that is currently the most distant confirmed object humans have ever found. It is 240 light-years across. It has a nitrogen abundance that connects it to the oldest stars in our own galaxy. It is surrounded by an ionized bubble that it carved out of the neutral hydrogen fog by itself. It was forming stars at a rate 10 times higher than its own recent average when its light left it, 13.5 billion years ago. The survey that found it asked whether this was a mirage or a miracle. The spectroscopy confirmed it is real. The question of what kind of miracle it is, what physics made it possible, what assumptions the models made that the universe did not share, what the distance between prediction and observation will eventually teach us about the first 300 million years of cosmic history, that question is the one the field is now. Carefully and with genuine uncertainty, and without sensationalism, working to answer. The universe grew up faster than we said it was allowed to. The evidence is overwhelming, and it keeps accumulating. Why it was allowed to, what specific combination of physics in the early universe permitted what the models called impossible, is what the oldest light, and the newest telescope, and the people working at the intersection of the two, are still slowly telling us. In July 2022, a message arrived with 3 words: "Look at this." The person who received it looked. He ran his software. 2 numbers came back. He nearly spilled his coffee. 3 years later, those 2 numbers have been joined by hundreds more. from dozens of galaxies. Confirmed across multiple instruments and multiple observing programs and multiple independent teams, and none of the new numbers have made the original problem easier to explain. They have made it harder, more constrained, more specific, more clearly a real property of the universe rather than an artifact of early imprecise measurements. The coffee was not spilled. The question has not been answered. Both of those facts are still true, and both of them matter.